Hello and welcome. In this video, we'll start to explore training the deep neural network. When we are working on a complex problem, such as detecting many objects inside images, we probably need to train a deeper neural network which contains more layers, and each layer contains hundreds of neurons. There are some problems we might encounter. Let's go through an overview about this video. First, we'll talk about gradient vanishing and gradient exploding. When we train neural networks, this can happen and cause bad effects. Second, we'll look into various random initialization approaches to mitigate the issue. Third, we'll look into the various activation functions. Let's get started. If you have watched the previous backpropagation video, now you can easily understand. If not, I have included the video link in the description below. I used this slide from the backpropagation. In this example, after we calculate the final loss from the output layer, we need to backpropagate the loss. For those layers closer to the output layer, we will call them higher layers. The weights of the higher layers can be updated with a relatively bigger number. For one layer before, the derivative includes more terms for the calculation, and each term is smaller than 1. The derivative results become even smaller. If you imagine we have 10 more deep layers, for those layers closer to the input layer, we will call them lower layers. The derivative results of the lower layers become extremely small and cause literally no updates after each iteration. This is called gradient vanishing. In some cases, we use different algorithms. The gradients can grow bigger and bigger during the backpropagation. The weights will be updated by incredibly large numbers, and the algorithm never converge. This is exploding gradient problem. The gradient vanishing and exploding can be mitigated significantly if we properly initialize the weights. Here, we won't dig into the complex math mentioned in the paper. Let's directly see the results. Here are different initialization methods. Based on different activation functions, the initialization is different. Glorot, he, and Lecomte are commonly used initialization methods. They are all named after the author. Fan-in stands for the number of neurons from the previous layer, and fan-out stands for the numbers of neurons from the next layer. Fan-average is the average of fan-in plus fan-out. Make sure weights are randomly initialized and their deviation equal to the calculation's results. Logistic activation function should use Glorot initialization. ReLU, leaky ReLU should use he initialization, etc. We can change the default Glorot initialization method to he initialization with the following line. Besides the random initialization, we can use activation functions to mitigate the gradient vanishing or exploding. As you might notice, we don't use the sigmoid function at the hidden layers for neural networks. The ReLU activation functions behave much better in deep neural networks. However, there are some issues with the ReLU function. This is a ReLU activation function. When the input is negative, the gradient is equal to 0. During the training, when neuron input becomes negative, the output of those neurons will be 0. And the gradient descent does not update weights because the gradient of ReLU is 0 when input is negative. Those neurons are literally dead. To solve this issue, a research paper in 2015 proposed a serious variation of ReLU functions. Let's first check out the leaky ReLU. It looks similar to ReLU function, but there's a small slope for negative inputs. Because of this slope, it prevents the neuron from dying. Some research papers said leaky ReLU always outperforms strict ReLU activation function. We can use a Keras package to easily create the leaky ReLU layers. The alpha parameter stands for the slope of the leak, and default is 0.3. We should make sure to use the heat initialization method. The issue about leaky ReLU is that it is not a smooth function. This part of the derivative is different from this part. If the optimum accidentally falls very close to zero, this discontinuity can cause gradient descent to bounce around the optimum. Recently, researchers came up with some different activation functions to address this issue. As you can see, those functions are continuity. Keras supports most of the implementation. These functions may converge faster than ReLU, but their computation is a little bit slow because of involving exponential computations. This wraps up our video. I hope you have better understanding about gradient vanishing, various weight initialization methods, and different activation functions. If you have any questions, please leave in the comment below. Thanks for watching. Please consider like and subscribe, and then I will see you in the next video.